Ladies and gentlemen, in this chapter, we want to talk about competence contrasts and the rheology of the Earth's crust. And this chapter will be delivered in two separate videos. In the first part, we will essentially talk about boudinage, which is the most common structure that illustrates competence contrasts, and the rheology of the Earth as a broader concept will be discussed in part 2. Competence is a technical term that refers to the resistance of a rock to undergo strain. Highly competent rocks would require high differential stress to respond in the form of failure, either brittle failure or ductile failure. Incompetent or less competent rocks are softer. They will fail by ductile or brittle failure at lower differential stress. In the ductile field, the rheology is essentially controlled by the dominant mineral species. For instance, in quartz-rich rocks, the mechanics of the rock would be essentially controlled by the plasticity of quartz. If feldspar is the dominating phase, for instance, in a metabasite, the feldspar rheology would control how the rock responds. Even a given rock type, let's say a gneiss or a mica schist, does not show the same rheology at different conditions. At low temperature conditions in the subgreen schist facies, a rock would show a different rheology compared to higher temperatures of perhaps the middle or upper amphibolite facies, because at low temperatures, plastic deformation processes are not as efficient. The rock would be harder compared to high temperature conditions where high plasticity would weaken the rock and make it less competent. If we have rock sequences that consist of different types of rocks, for instance, metabasites interlayered with quartz-dominated rocks, this would lead to competence contrasts, because quartz-dominated rocks in mid-amphibolite facies conditions, for instance, would be much more plastic and therefore less competent than metabasites, where the rock mechanics, the rheology, is controlled by mafic minerals or feldspars, which under these conditions might still be less plastic and therefore more competent. Let's make an example. Here we see a differential stress strain diagram, and we see here the results of strain experiments carried out at low temperatures, at green schist facies temperatures, or in the amphibolite, upper amphibolite, and granulite facies. And we can see that the rock A here required something like 15 or 1600 megapascals differential stress to fail and to break under low temperatures, 25 degrees. At 300 degrees, still quite substantial differential stress was required to deviate from the linear elastic behavior to start and fail, and steady state flow eventually was reached at perhaps 1400 megapascals differential stress. At higher temperatures, we see that the curve is shifting, and lower differential stress is required to allow plastic flow in these rocks. In the granulite facies at 800 degrees, we see at about 200 megapascal differential stress, we achieve steady state ductile flow. Let's compare that to rock B, and let's say rock B is different in its mechanics, and similar kind of behavior is achieved at lower temperatures. We see here that at 200 degrees, the rock fails at about 1400 megapascals, and at 300 degrees we require just around 1000 megapascals to achieve steady state flow. And if we compare the behavior of rock A and rock B, we would see that At 300 degrees Celsius, we find that rock B requires a lower differential stress to undergo strain. The difference is even larger at 500 degrees Celsius. At 500 degrees Celsius, rock A requires more than 1000 megapascals differential stress to undergo strain, whereas rock B starts to fail and accumulate plastic strain at already about 500 megapascals differential stress. So that means rock B is clearly less competent. It deforms more easily at the same temperatures. Let's assume the situation where competent layers are interlayered with less competent ones. And here in this example, we see only the competent layer. Let's assume on top and underneath this competent layer, there is less competent, softer rock. And here we see the result when this layer undergoes layer parallel lateral stretching. We see here the stretching will break up the competent layer into rod-like bodies that we see here. There is a linear fabric element along the breakage that would be the Boudin lines, and the linear fabric that we would observe in the field is referred to as necklines. The individual rod-like bodies that we see here, that is what we refer to as boudins. So during that process of boudinage, we see that a competent layer undergoes brittle or semi-brittle failure during the lateral extension. The less competent layer on top and underneath, not shown here in this example, would undergo uniform plastic failure without a brittle component and without forming the boudins that we see here. In the illustration here at the bottom, we see some of the less competent over and underlying rocks, and we see here plastic flow is much more effective, and we see that the gaps, the necks between the boudins are filled by plastic flow that forms these kinds of fold-like geometries. That is what we refer to as a neck fold. And very often, if a hydrothermal fluid is present, we would find the precipitation of minerals from these hydrothermal fluids in the necks between the more brittle boudins. This is potentially an economically important process because boudinage is a process that also can affect rocks at large scale. Imagine that these competent layers here are perhaps tens or hundreds of meters thick, and intense hydrothermal activity precipitates minerals here in these boudins, and we know that many commodities are deposited from hydrothermal fluids. If, for instance, the hydrothermal fluids in that region that precipitate minerals are saturated in gold, you might actually find gold deposits in the necks of megaboudins. If it's a small-scale process, of course, this would economically be irrelevant, even if you get some elevated grades of gold and other commodities in such places. If the extension is not perfectly parallel to the competent layer, we get a rotation of these boudins. And here we see a two-dimensional cross-section through a sequence of layers. The white one is the most competent one that was broken up into rectangular boudins. And in 3 dimensions, you need to think of these rectangles here again as rod-like bodies that extend into the 3rd dimension that we don't see on this photograph. Important is the rotation, and if you see such rotated boudins, you know that the extension direction was not parallel but slightly oblique to that competent layer. Here we see a structure that is closely related to boudinage. Boudinage on the left-hand side is characterized by the disruption of a layer. Separate boudins have gaps in between, and a once coherent layer shows disruption into separate boudins with gaps in between separating them. In pinch and swell structures, this is not quite the case. We still see the coherence of the more competent layer, which is thinning out in the pinched areas and is increasing in thickness in the swell part of the pinch and swell structure. The swell part of the pinch and swell structure is named in a slightly misleading way because what we see here is a thinning out that is less intense than in the pinched structure. Initially, the layer may well have been thicker than what we see. The difference between the swell part and the pinched part of the structure is the different extent of thinning, which is more intense in the pinch and is less intense in the swell part. But throughout the layer, we can expect that a certain amount of thinning has taken place during lateral stretching of that layer. Why does lateral stretching form boudinage in some situations and in other situations pinch and swell structures? The reason for that lies in the magnitude of the competence contrast between the more and the less competent layers, and we see that illustrated here on this slide. Let's assume here the grayish rock is a soft rock, is a rock of low competence, and it is interlayered with different kinds of layers that show different amounts of competence contrast. And let's assume the competence contrast between the gray and the white layers increases from bottom to top. This means the layer here on top is the most competent of all of them, and the layer here on the bottom has the same low competence as the gray layers that host these more competent layers. If we apply lateral extension to this sequence of layers, we will find that the uppermost layer responds by the formation of tensile fractures with very little lateral extension. We see that starting here already in the situation at the top, and we see that these boudins that have formed are separating further and further from each other the more we stretch the rocks laterally. Looking at the second layer here, we also see tensile fractures start to form, but the spacing of these tensile fractures is larger. Accordingly, the boudins are a little bit wider, and we see that here slightly different structures are forming. We see a very prominent fish head, or also called fish mouth geometry, in these boudins. The third layer that we see here just starts to thin out with moderate extension, and with increasing extension we find pinch and swell structures. At high lateral strain, these pinch and swell structures start to grade into boudins, and if we would have a fourth image on this sketch, the pinch and swell structures would grade eventually into boudins. And these boudins would have very acute interface angles towards the boudin necks. The layer at the bottom, which has the same mechanical properties as the incompetent host layers, just uniformly stretches because there is no competence contrast between this layer and the hosting darker layers. Accordingly, we can use the shape of boudins and of pinch and swell structures to give a semi-quantitative estimate of the amount of competence contrast between the competent and the less competent layers. If we see rectangular boudins or fish head boudins, we know that the competence contrast was relatively high. If we see pinch and swell grading into boudins, and if we see very sharply pinched out boudins with a very acute angle towards the boudin necks, we know that the competence contrast was relatively small. Let's have a look at some examples from the field. Here we see sills of pegmatites hosted in muscovite schists, and we see pinch and swell structures, and we see boudins. But we see that the interface angle between the schists and the pegmatite boudin is highly acute. So this interface angle is a very small angle, and that indicates a low competence contrast. The pegmatite is more competent, but not much more competent compared to the hosting schists under the conditions of deformation. Here on the left-hand side, we see similar geometries, strongly pinched out boudins and pinch and swell structures still present. The white layer here is the more competent one, but the competence contrast to the hosting dark gray rock is relatively small. Here we see a folded layer, and that already tells us that folding and boudinage along the limbs of folds is an important process. We are coming back to that a couple of slides later. Also here we see pegmatite sills hosted in muscovite sillimanite schists from the Bushman land group in South Africa. But here the shape of the pinch and swell or boudins, here magnified, is different. The interface angle of these boudins is much larger, and that tells us that the competence contrast between the pegmatite sill and the hosting sillimanite schists is larger than in the previous example. On the right-hand side image, we see a close-up of this area here, of the necking area between these two pinch and swell, soon to be boudins. And we can see here the typical neck folds of the less competent aluminous schist folding into the gap between these two pinch and swell bodies of the stretched pegmatite. We also see that here from the top. Also here, plastic flow allowed the muscovite sillimanite schist to fill the space between these two pegmatite bodies that are just about to disrupt. So technically this is still a pinch and swell structure because the bodies are still connected by a thin bridge of pegmatite. Here we see an example from Elba Island in Italy. This is an interlayering of amphibolite, which is the highly competent blackish layer, interlayered with biotite mica schists that we see here on top and on the bottom. And we can see the expression of the competence contrast by observing a spaced foliation and intense ductile stretching of quartz-rich domains in this mica schist, as opposed to brittle failure in the amphibolite layer, where we see here sharp tensile fractures are forming. We also see that some of the fragments of the boudins start to rotate, which indicates that the stretching is not quite parallel to the layering here. Some form of oblique stretching is responsible for the formation of the structures that we see. Highly ductile shearing in the biotite mica schists, brittle failure and boudinage in the amphibolite layer. The high competence contrast is indicated by the angular geometry of the boudins. Let's investigate the relationship between boudinage and folding. Here we see an example from Hobbs, Means, and Williams' beautiful textbook on structural geology. This is a classical example of the formation of boudins along the limbs of folds. We see that no boudins are present in the hinge of folds, where we see intense layer thickening. We see that here in the more ductile layers that show clearly a lower thickness along the limb compared to the thickness of the layer in the hinge. If we assume that this fold has formed by lateral shortening, that would mean S3, the direction of maximum shortening strain would be roughly horizontal, forming this buckle fold. That would imply that the maximum stretching direction is vertical. And that would mean that the layers in the hinges of the folds are more or less parallel to the shortening direction. That does not help to make boudins, because boudins require that the stretching occurs more or less parallel to the layer. And that applies to the limbs of the fold. In the limbs of the fold, obviously, the layer orientation is different, and we assume that the shortening direction is the same as in the hinge. If we apply this to the limb of the layer, we see we have perfect conditions in order to form boudins. We have stretching more or less parallel to the layer and shortening more or less perpendicular to the layer. These rod-like boudins that we see here indicate that there is not much strain taking place along the axis of the boudin, which would imply that we are looking at plane strain conditions. In plane strain, the intermediate principal strain axis remains 1, and that would mean neither stretching nor shortening occurs along the boudins. The stretching happens in this direction, the shortening happens perpendicular to the layer in which the boudins form. Let's have a look at the Flynn diagram. Here we see that illustrated along the line of plane strain. One axis remains constant. That would be the S2 axis. The S3 axis shortens, the S1 axis stretches, and that is the strain type that would form these rod-like boudins. Along the rod axis, no strain occurs, neither stretching nor shortening. The boudin type that forms under oblate strain conditions would look like that. Here we see a different type. We see stretching occurs in two directions. S1 and S2 both are undergoing elongation, and that would break up our competent layers in two directions at the same time. Shortening takes place perpendicular to the layer. Stretching occurs in two dominant directions, and that breaks up the competent layer into these kinds of rectangular boudins with two boudin axes that are roughly perpendicular to each other. This type of boudinage we refer to as chocolate block or chocolate tablet boudinage. Chocolate block boudinage is quite common in the field, but not often well exposed. Here we see an example that shows us a kind of a glimpse how chocolate block boudins look like. We see here this dark gray blackish layer of dolomite, which underwent chocolate block boudinage, and the gaps were filled in by calcite, which is white. And we can see here necklines oriented towards us and from the left to the right. These are the two necklines of the chocolate block boudins, which show these kinds of rectangular bodies that we see here distributed in that area. This is one of the best images of chocolate block boudinage that I could find. Perhaps you find better ones if you look through the internet, or if you are lucky, you might come across chocolate block boudins in the field. Whenever you see boudins in 2 dimensions, try to get a 3-dimensional view onto the layer, perhaps you actually are dealing with chocolate block boudins. For that, you need to have a look onto the competent layer, which is not always as nicely exposed as we see here. So in principle, what you're looking for are rectangular boudin bodies separated by two different necklines that are at high angle to each other. Let's investigate what happens to other strain markers when layer parallel extension takes place. Let's consider the deformation of a block with a competent layer, here shown in black, that is intersected by two magmatic dikes at high angle with each other. And also these dikes are more competent than the hosting rock that is shown here in beige color. Under plane strain conditions, we would shorten in one direction, let's say vertical shortening, and lateral stretching in the S1 direction. And along the third principal strain axis, S2, we change nothing. We neither extend nor we shorten. What would happen to the competent layer is simple boudinage. Rod-like boudins would form. They are shown here underneath our block. These kinds of boudins would form in the dark competent layer that is undergoing layer parallel extension. What happens to the magmatic dikes? There is magmatic dike 1, magmatic dike 2. Magmatic dike 1 would show folding. We see here these folds are forming because this rock is undergoing vertical shortening. We don't see any response of dike number 1 in the direction of S2 because along S2 no strain takes place, neither extension nor shortening. The response of the second dike here, that is oriented perpendicular to the first one, is different. This dike runs along the maximum stretching direction and it runs perpendicular to the S2 direction. And again, we would see vertical shortening, which leads to the formation of the folds that we see here on the right-hand side of our reference block. But we also would see that this dike would undergo stretching parallel to its orientation because it runs parallel to S1. This stretching parallel S1 would form the boudins that we see here. So think of this dike as a folded dike, but these folds are segmented into folded rods. We are going to see how that might look like in one of the next images. Let's investigate what happens under pure flattening or oblate strain. Under oblate strain, we find that the stretching parallel S2 is as large as the stretching parallel S1. And that will produce different structures. First, our competent layer parallel to S1 and parallel to S2 would undergo chocolate block boudinage, because the stretching in this S1 direction is as large as it is in this S2 direction. That means our competent layer undergoes vertical shortening and it's segmented along two perpendicular necklines into these rectangular chocolate block boudins. What happens to the magmatic dikes? Dike 1 that we see here is undergoing folding because it is parallel to the shortening direction, S3. It also undergoes boudinage. We see that here it is undergoing boudinage because it is oriented parallel to S2, and S2 in this case, is undergoing extension. It stretches. So the stretching will dismember this magmatic dike that is undergoing folding in S3 direction in the direction of S2. The same happens with dike number 2. Dike number 2 is parallel to S1. S1 is undergoing stretching and it is undergoing folding in the direction of S3. We need to consider a third type of strain, and that would be pure constriction or prolate strain. In prolate strain, the stretching parallel S1 is compensated by equal shortening along S3 and S2. In prolate strain, only S1 is undergoing extension. All other directions undergo shortening. And that again has consequences for the structures that we form out of this initial situation. What we see is boudinage of the competent layer parallel to S1, because that is the direction of stretching. We also see that these boudin rods undergo shortening in the direction of S2, because S2 and S3 are equally shortening in pure constriction. And here we see how these rods then would look like. They are separated from each other because of the boudinage parallel S1, but they also are shortened because they are oriented parallel to the S2 shortening direction. This kind of geometry we also would have observed in this example here for the magmatic dike number 2. Also, this magmatic dike is broken up into rod-like geometries and is undergoing folding because it happens to be parallel to the shortening direction and parallel to one of the stretching directions. Also, the dikes that we see here in the pure flattening example would have this kind of geometry. They would be segmented into rods, and these rods would have undergone folding. What happens to dike number 2? Let's start with dike number 2. Here we see exactly the same behavior that we have seen in this example here. We see the dike is dismembered into individual boudins, and these boudins undergo shortening because they are parallel to one of the shortening directions, S3 in this example. The structures for dike number 1 are even more complex because dike number 1 undergoes folding in 2 directions at the same time. Dike number 1 is in an orientation where it is shortened parallel S3 and it is shortened parallel to S2. That means we are forming 2 hinges at the same time. We form the hinges that we see here on the front of the block, and we see folds are also forming with hinges that are steeper oriented. We see folds also developing if we look from the top onto that dike. So what we can learn from these examples is that the strain that is manifested in rocks strongly depends on the orientation of the strain marker. We see here 3 different strain markers, and we see their response to stretching and to shortening depending on which strain type affects them. The best example is probably our competent layer forming simple boudins in that case, chocolate block boudins in the pure flattening example, and in the pure constrictional example we see folded rod-like geometries forming from our competent layer. I'm aware of the complexity of the structures that we see on this slide, but you will benefit a lot studying carefully what happens under which type of strain, depending on the orientation of the strain marker. We can learn from these examples here that folding, which is a typical structure of shortening, can very well develop at the same time like boudinage, which is a typical structure for extension. Extension and shortening normally happen at the same time. They act in different directions in the same rock, and if you find strain markers in the right orientation or in a variety of orientations, you will observe in the field structures of shortening and structures of stretching in the same outcrop. Depending on orientation of your strain marker, the one or the other might happen. So this is the end of the first part of our chapter on competence contrast and the rheology of the Earth's crust. We are continuing in the second part with the rheology independence on pressure and temperature and composition of rocks. Thank you very much.